differential equation. What does differential mean? It means derivative. So this means derivative equations. We're given a derivative equations such as y prime equals to 2x is a derivative equation. Dy over dx equals to e to the x is a derivative equation. So basically we know the derivative function and we're trying to find the antiderivative, okay? So it is kind of like finding the antiderivative, but the only difference in this lesson is that we get to find out what c is. Before this lesson, we found the antiderivative of a derivative function, but we always have that plus c. So in this lesson, we get to fill in what that plus c is. Okay? All right, so let's get started. A differential equation, those are some examples. Is another way to think of it is these are the derivative functions. An equation involving derivatives, so these equations involve first or second derivative. From time to time, you will be given an initial condition. This is some known value about the original function. We call that the initial condition. And then you will be asked to find the solution. To find the solution basically means to find the antiderivative function and also fill in what c is, and that's what it means by finding the solution. So the word solution might come off as like a number, but it's actually not. It's actually the original function with c filled in. Okay? Now I listed some general steps on how to solve a differential equation. So let's walk through them. First, we will be gathering the same variables on opposite sides of the equal sign. So if there's anything that involves an x, will stay on the right side of the equal sign. Anything involves a y stays on the left side. All right. We will then integrate both sides with respect to the appropriate variable. And then after we integrate both sides, then we will find their antiderivative and then we will solve for them. Okay. So let's get started with a few examples, and I think you will get the hang of it. Solving differential equations. So here is an example of a differential equation, which means that you're given the first derivative and you're also given some initial condition. This is our initial condition. So we know something, we know a point on the original function, but that's all we know, right? And when we solve it, we're trying to find a solution, which is the antiderivative function with c filled in. All right, so how do we solve it? Well, to solve it, we begin by gathering the same variables on the same side, on the same side of the equation. What does that mean? Well, I will be putting anything that involves an x on the right side of the equation, anything that involves a y on the left side of the equation. So let's do that. Let's go through the first step. So gather the same variables on opposite sides of the equal sign. All right. So here's the first thing that I'm going to do. This is the right side. Okay, that's the right side of the equal sign, and that's the left side of the equal sign. So anything that involves an x, I will put that on the right side. So first of all, we know that originally there is a 3x squared on the right side. Now, what I will need to do is I will need to move the dx to the right side. And the way how I do that is I multiply both sides by dx. Okay, so those cancels out, see? So what I have done is I have moved the dx to the right side. So anything that involves an x stays on the right side. Anything that involves a y stays on the left side. Good. That's the first step. Second step, integrate both sides with respect to their variable. So here's what you do. You just integrate both sides. And that's what we mean by integrating both sides. Okay? All right. So once we have integrated both sides, we are going to integrate the left side and then integrate the right side. So for now, if you don't mind, I will be covering this up, and I will integrate the left side. All right? When you integrate the left side, this is the same as the integral of 1 dy, and that equals to y. That equals to y. Okay. Equal, and then cover this up. Now integrate the right side. Integrating the right side with respect to x, we will get x to the third, and then we do a plus c. See? So guess what? Well, when we're trying to find a solution, this is a differential equation. This is an initial condition. When we solve, we're trying to find a solution, and a solution is the antiderivative function with the c filled in. Yay, so we do have a y function. Now we need to fill in that c, and that's our solution. So how do we fill in that c? Well, very simple. We now refer to our initial condition. So I dot c stands for initial condition. When an initial condition is given this way, it means that x equals to 0 and y equals to 2. Okay, x equals to 0 and y equals to 2. This is our initial condition, and that will allow us to find out what c is. So let's go ahead and plug in 2. Okay. Simplify, and we know that c equals to 2, right? c equals to 2. Now we fill that in. We fill in the value of c. And therefore, our solution, we call this a particular solution is y equals to x cubed plus 2. And we're done. Okay, so this is the original function. And think about it, if you take the derivative of this function, you will get that. There you go. Okay, so it's actually not bad, right? It's very similar to antiderivative, but now we just have to fill in what c is using the initial condition. All right, so let's do more examples. Here's another one. How do we start? Well, we begin by moving all the anything that involves an x to the right side and anything that involves a y to the left side. So we will begin by multiplying both sides by dx, and that will get rid of the dx on the left side. And afterward, we will then integrate both sides. So we will integrate both sides. Okay. When we integrate the left side, we get y. When we integrate the right side, we get x to the 8, and there's a 1/2. So I'm using the power rule, and that's how I got 1/2 plus c. All right. Now we bring in our initial condition. So initial condition, and hopefully by reading that initial condition right here, when x equals to 0, we know that y equals to 4. Okay, that's our initial condition. All right, it's given right there. We take that, we plug it in here, and that allows us to find out what c is. So 4 equals to 1/2 times 0 to the 8 plus c. c once again equals to the y value, so c equals to 4. And last but not least, we fill this in, and this is our particular solution. So particular solution. So you might wonder, well, Mr. Nguyen, if you keep calling this solution particular solution, then is there another type of solution? Well, the answer is yes. When the c is not filled in, it's called a general solution. General solution. There you go. Nice job. You solve another differential equation. Yay! Let's move on. Notice that the first derivative can be expressed in many different ways. We can express it as dy over dx. We can also express it as y prime, but we have to keep in mind what the variable is. In this case, the variable is t and not x. Okay? So when it is expressed something else other than this, I like to change it back to this notation. So why don't you do this? Rewrite the problem as dy over dt, because the variable in this case is t. All right? The next thing we have to do is we have to separate all the t's to the right side and then all the y's to the left side. And the simple way to do that is to multiply both sides by dt. And if we did it right, this is what we are going to get. Okay, dt, there you go. All right, remember, when we're solving a derivative equation, differential equation, we're trying to find the antiderivative. And we're using this condition to tell us what c is. And that's what we call the solution. So once you have separated all the variables, then the next thing we do is we integrate both sides. So draw an integration symbol like this. This tells us to find the antiderivative of each side. So we cover this up, we find the antiderivative of that. Remember, the reason why this is y is because this is the antiderivative of the number 1, and the antiderivative of 1 is y. Because you take the derivative of y, you get 1. Okay? So you get y, and then over here, when we find the antiderivative of sine, that is going to be negative cosine. So negative cosine, okay, and then leave the inside alone. When we find the antiderivative, we always multiply it by 1 over the derivative of the inside, which is pi. All right? And then we add in a plus c. Add in a plus c. So this is called the general solution. Before c is filled in, it's called the general solution. So now we will use our initial condition to find the particular solution. So our initial condition, x equals to 2, y equals to 2. That's what it says right here, right? X is inside the parentheses, y is the value outside the parentheses. So we take that and we plug it in here, and that allows us to find what c is. So let's see, 2 equals to negative 1 over pi cosine of 2 pi, because, I'm sorry, this I should have said t and y, t, okay, because that's t. So plus c. So then what do we have here? Now cosine at 2 pi is 1. Cosine at 2 pi is 1, so we're just going to get that. Now to solve for c, we add both sides by 1 over pi. So then this is c. Okay, this is c. Now once we found c, then we plug that in there, and so we get the particular, another word for particular is unique solution. So our particular solution, our unique solution is y equals to cosine of pi t, and then we fill in the c value, which is 2 plus 1 over pi, and we're done. Now if you want to verify to see if this is the derivative, then you can always take the derivative and you will get that. Okay, very good. Let's do more examples so that you can develop your skills. And if you think you're right, you can do it by yourself, then do the next 2 examples by yourself, and then check the answers, pause the video, check the answers with me, and see how you did. So again, I would change this so that it says dy over dx, because this is dx, tan e to the negative 2x, all right? First thing I am going to do is I will separate the variables. So move the dx to the right side of the equation, so that it looks like that. The next thing I do is, once I have separated the variables, I will integrate both sides of the equation. The left side gives me y. The right side, when you integrate this, when you integrate a constant, it stays where it is. When you integrate e to the negative 2x, you get itself, and then you multiply it by 1 over the derivative of the inside function, which is this, and the derivative that is negative 2, you add in a plus c. Okay? And now we simplify that, so we get negative 5e to the negative 2x plus c. This is what we call the general solution, and if we and by the way, we don't have the initial condition, so we can't find a unique or particular solution. Therefore, this is just our general solution, and we're done. General solution, and we're done. Okay, very good, very good. All right, let's take a look at the next example. We are given the second derivative, so be careful. Okay, we're given the second derivative, and we are trying to find the original function. Okay, the original function. So here's what we do. We go d square y over dx square is equal to 3x plus 2, right? 3x plus 2. So when we will now separate the variables like this. 3x plus 2 dx square, like that. Okay. Now when we integrate these, it might look a little bit the symbol might look a little weird. Okay, the symbol might look a little weird, but keep in mind that this is the second derivative. So when we integrate this, we actually get the first derivative. So this is maybe solving for the first derivative, okay, or y prime, because we're given y double prime. So when you solve the differential equation, you're finding the antiderivative of it, and that means you're going to get y prime, right? So why don't we do this? Why don't we just for now just label it like this for now, so that you're less confused with the symbol. And we're gonna integrate both sides like this. When you integrate this side, you get y equals 2. When you integrate this side, you get 3 over 2x squared plus 2x plus c. Okay, but keep in mind that we're just using the dummy variable dy dx to help us solve. But this equation is actually the equation of y prime. Okay, it's y prime because we know the second derivative. So when we integrate, we will get the first derivative, and then if we integrate again, then we get the real function. So I feel like I have used this variable enough. So now I'm going to make it right. So I'm going to call this y prime because it is y prime, right? Because you have the second derivative. You're given the second derivative, and you're taking the antiderivative, so you should only go back one step. So this is the first derivative. And we will plug the initial condition in. So the initial condition is y equal to y prime equals to the initial condition is x equals to 0, and then y prime equals to 1. We take these and we plug it in there. So we have 1 equals to 3 over 2, 0 squared plus 2 times 0 plus c. So c comes out to equal to 1 because these cancels out. So then when we plug that in, we're going to get y prime equal to 3 over 2x squared plus 2x plus 1, and that's y prime, right? Now, I didn't specify what I'm looking for, right? So when I said solve for this, it means that you would solve and find the general solution. And the reason why it's the general solution is because we don't have another initial condition to fill in to satisfy the c of the original solution. So here's what I would have to do again. I would have to integrate this again, and that allows me to find my general solution. So if I were to integrate that again, okay, then I can find my my general solution. So this would become 3 over 6, and that would be 1/2. This would be x squared, and this would be x, and then plus c. Now this is my general solution, and that's the best I can do because I can't fill in the c. I don't have another set of conditions to help me find out what c is to finish the problem. So that's the best I can do. All right. Now the last thing is, well, it's really not the last thing, but I want to show you more challenging problems regarding differential equation. We're going to keep the method consistent on our strategies on how to solve differential equations. So keep in mind that when we do, we have to separate the variables. Anything that involves an x stays on the right side, anything that involves a y stays on the left side, and then we solve, okay? So using that same method, let's take a look at some more challenging examples. Now notice that this is the first example where you see both x and y together. So here's where the separation is really needed. We begin by separating all the x's to the right side, moving all the x's to the right side, and moving all the y's to the left side. So here's what I am going to do. If I want to move the dx to the right side, then I would need to multiply by dx. So it would look something like this. dy equals to 6xy squared dx. And my next step is to move all the y's to the left side. And the way how I move the y to the left side is I divided both sides by y squared. And dividing both sides by y squared will give me something like this. All right, so guess what? Well, I have separated my variables. And once I have succeeded with separation of variable, see, then the next thing I do is I integrate both sides. So here I am going to integrate both sides, integrating also the right side. Now, when you integrate this function, you need to see if it has an antiderivative, and it is, because that's just y squared. And to find the antiderivative of this, you add 1 to the power, and then you divide it by the new power. So when you add 1 to the power, you get y to the -1, and then you divide it by -1, right? And then when you do it over here, you get 3x squared plus c. Now when you simplify this, you will get negative 1 over y is equal to 3x squared plus c, because this gets moved down and so on and so forth. So the next step is we're trying to solve for y, right? The next step is we're trying to solve for y. So what we have to do here is we will have to multiply both sides by y, and then divide both sides by 3x squared plus c. But this is where I'm going to stop, and this is where I will find what c is, because I do have an initial condition. So I'm going to take that and plug it in here and find out what c is right now. So we know that our initial condition is x equals to 1 and y equals to 1 over 9. So I plug those in there, and I get, when you plug 1 over 9 in there, I am going to get -9 on the left side, because 1 divided by that is not -9. And when I plug 1 in here, then I get 3 times 1 squared plus c. So c is going to be -12. C is going to be -12. I found what c is, so now I go back and I fill in my c. So 3x squared minus 12, okay? 3x squared minus 12. And now I solve for y. And if you solve for y correctly, then here's what you should get. Now try to get this answer, and then if you're having a hard time, then let me know and I will show you how I did it. But here's what I did. I multiply both sides by y. If I multiply both sides by y, then I still have a -1 down here, right? But I have a y on the right side. And then I divided both sides by this guy, and that's what I got. Okay? So I solve for y, and I'm done. That would be the particular solution for my differential equation. See how it's getting a little harder now? All right, let's do another problem. First thing is I have to separate the variable, so multiply that to both sides. So here's what we get. Okay, and then I have to move this to the left side, and to do that I divided both sides. So I will divide both sides by y minus 2 x squared dx. Okay, and now I've separated the variables, so I'm going to integrate both sides. So integrating the left side and integrating the right side. Now when I integrate the left side, if you like, you can use u substitution to integrate the left side, but after you have done it correctly, you will get ln of y minus 2, and that's equal to x to the third over 3 plus c. Okay, remember, we're trying to solve for y. So here's the next step. Whenever there's an ln involving in an equation, you may get rid of the ln if you raise both sides by e. So I will raise both sides by e. That's what it's going to look like. Okay, when you raise both sides by e, they drop out, so you have y minus 2. Now remember, this is very important, laws of exponents. What does it say? It says that whenever you have whenever you have and it could be any base and not just e, but whenever you have e raised to the a plus b, then it can be separated into e to the a times e to the b. And that's exactly what I'm going to do here. I'm going to separate this so that it's going to say e to the x to the third over 3 times e to the c. Now e to the c is just another constant, so I'm going to call it another. I'm just going to call it another c. So I'm going to call this a c, and I'm going to put it in the front like this. So this c will be a little bit different from this c, and you can kind of tell because the size of this c is a little bit bigger. Okay, now we use the initial condition, which is right here, to find out what c is. So this tells us that x equals to 0 and y equals to 0. So y equals to 0. So initial condition, x equals to 0, y equals to 0. Okay, plug those in, which I did, right? Plug it in here. Y equals to 0, x equals to 0. Plug those in. C, we're going to get e to the 0, and everybody knows that e to the 0 is 1. So c comes out to be negative 2. Plug negative 2 in here, and you're done. So y minus 2 equals to negative 2 e to the x cubed over 3. We add 2 to both sides because we wanted the solution, which means y has to be solved for. So we solve for y, and we add now our solution. So this is what we call the particular solution, or the unique solution. Okay. Try the last example yourself, and then we will go over it tomorrow.